Hello, MGA. My name is Zuheir Altamimi. I am a research director at National Institute for Geographic and Forest Information, IGN, but also at the Institute of the Physics of the Globe that is located in Paris. I'm happy to be with you here to brief you about geodetic references. It will be a short presentation. I will focus mainly on the International Terrestrial Reference Frame, the ITRF. In particular, the latest release of the ITRF called the ITRF 2020. This is the outline after an introduction regarding reference frame representation for an Earth that is deforming constantly. User needs. The ITRF itself, it is GNSS Continuous Development and Improvement, the ITRF 2020, and it is innovation in modeling non-linear station motions, seasonal signals, and post-seismic deformation. The ITRF 2020 kinematic model and it is usage. So what is a reference frame in practice? It is an Earth-fixed centered reference frame that allows you to determine station positions, but also satellite orbit as a function of time. When we analyze space geodesy data, we have to take into account relativity theory, the forces that are acting on the satellite, the atmosphere, Earth rotation, solid Earth, and ocean tides. And we realize, of course, that the Earth is deforming with linear and non-linear variations, and therefore station coordinates are a function of time. And despite this complexity, we reach nowadays, in terms of accuracy, a few millimeter in position and a few tenth of millimeter per year for the best stations. But in any case, when we compute a reference frame, we have to specify clearly its origin, its scale, and its orientation. Now, these are the space geodetic techniques that contribute to the ITRF: VLBI, SLR, GNSS, and DORIS. And in terms of motions of the Earth that is deforming, we have nearly linear motion, tectonic motion, post-glacial rebound, and non-linear motions like those are induced by loading deformation due to atmospheric pressure, hydrology, and ocean circulation. We have also co- and post-seismic deformation, as we see here in this example, co- and post-seismic deformation, transient deformation, volcano eruptions, and local events. Now, in terms of reference frame representations, we have two categories of reference frame. The first one is the long-term linear frame. This will give you access to mean station positions at a reference epoch T0 and velocities. And you have the equation here that allows you to compute the position of your station at any epoch T, starting with its position at T0, plus the velocities times the time interval between T and T0. And that's what we call regularized position with piecewise linear function. And this is fundamental for science and operational geodesy application. The second category is non-linear reference frames, and here we have two subcategories. The first one is an augmented parametric reference frame. It means long-term frame plus non-linear parametric functions, and this is the case, the ITRF 2020. I will come back to that in this presentation. The second subcategory is what we call non-parametric reference frame. It means time series of quasi-instantaneous reference frames. We have daily or weekly representations, and the non-linear motion of the stations will be embedded in the time series. But this type of representation still rely on the ITRF for at least the orientation definition. Now, the International Terrestrial Reference Frame is realized and maintained by the ITRF Center, hosted by IGN. It is computed by combination of DORIS, GNSS, SLR, and VLBI, weekly, daily, or session-wise solutions. So we start by analyzing the time series using the CATREF software we developed at IGN for this purpose, and we provide to the users station coordinates, station velocities, and other parametric models. Now, the IHRF is fundamentally based on collocation site. This is a picture of a fundamental collocation site in Yarragadeen in the Western Australia, where you have all the 4 techniques collocated together: GNSS, SLR, DORIS, VLBI, and even gravity measurement here. So this is, for instance, the SLR instrument that is here since about 40 years. And we have a very nice time series of that SLR telescope. And in addition to space geodesy input data, in order to be able to compute the IHRF, we need what we call local survey, which means the differential coordinates between the reference points of the different instrument at collocation site. This is a crucial information that is necessary for us in order to be able to connect the techniques together and to compute the IHRF. Now, why is the IHRF needed? We have operational geodesy applications, positioning, real-time or a posteriori, navigation, aviation, maritime, terrestrial, but also national geodetic systems and frames. And nowadays, most of the countries use the GNSS technology to modernize their national reference frames. Using GNSS require the availability of the orbits, and that is available via the IGS products. The IGS stands for the International GNSS Service, but also the IHRF. Of course, I have no time to develop how to connect a national reference frame to the IHRF. This is a big issue that needs more time to explain. And here we have many users. Another category of users is for the GNSS-specific reference frames. Within the International Committee on GNSS, the ICG, we heard from the GNSS providers that their GNSS-specific reference frames are aligned to the IHRF. This is the case of the GTRF for Galileo, WGS80 for GPS, PZ90 for GLONASS, the Chinese Geodetic Coordinate System 2000 for Beidou, and the Japanese Geodetic System for QZSS. And these are normally all aligned to the IHRF in order to ensure interoperability of these GNSS systems. Now, we have also a variety of scientific applications, starting with the precise orbit determination, Earth rotation, tectonic motion and deformation, post-glacial rebound, ice melting, etc., etc. And for that, we need the IHRF to be, in terms of its defining parameters, origin, scale, orientation, accurate at the 1 millimeter and 0.1 millimeter stability per year. Now, we need also to do continuous observations in order to follow these scientific applications, especially those are related to geodynamic processes that affect the Earth's surface. Now, there is a number of resolution on the ITRS. The ITRS is the International Terrestrial Reference System, and the IHRF is the frame that realized the ITRS. So there is a number of resolution and recommendation by IUGG, CGPM, ICG, of course, IUGG, UNGGIM, and ISO standard on the ITRS. ITRF is available today. Now, the strategy to compute the IHRF 2020, we have, as I said, time series as input. We have local ties at collocation sites, and at these collocation sites, we equate station velocities and we equate seasonal signals. And then we analyze the time series all together and we determine station coordinates, velocities, station coordinates, velocity, post-seismic deformation parametric model, and seasonal signals and Earth orientation parameters. In the computation of the IHRF 2020, we specify its origin, which coincides with the SLR frame origin, the center of mass. The scale is computed by the average of SLR and VLBI scales, and the orientation is by alignment to the IHRF 2014. Now, the innovation of IHRF 2020, for instance, the impact of loading effect, as you see here as an example, a station in Brazil near the Amazon. After removing the linear trend, we see a very nice seasonal signals, especially in the up component, which is of course due to hydrology. We modeled that using a sine wave function. And after post-seismic, for sites that are impacted by post-seismic deformation, here the map shows you the location of 65 epicenters that impacted 118 IHRF 2020 sites. And we modeled that using parametric models, logarithmic function, exponential function, the combination of two, or two exponential or two logarithmic. Just an example of Tsukuba, a site in Japan where we have GNSS and VLBI instruments. Here I am showing here the trajectory of GNSS instrument in the northeast component. In blue is the original time series coming from GNSS. In green is the velocity due to tectonic motion. And in red that you see here is the parametric model we fitted using GNSS data. And you can see also seasonal signals, as I said, due to loading effects. Now, when we look to VLBI instrument, we see that the parametric model in red fits perfectly also the VLBI time series. So this ensures interoperability of the parametric models that we provide to the users in terms of post-seismic deformation. Now, the IHRF 2020 is an augmented parametric reference frame, and this is the kinematic model. You have in one side the linear part of that model, position at T0 and velocities, and then the non-linear part, which has two components, the post-seismic deformation parametric models, PSD, and the seasonal signals that are expressed in the center of mass of SLR frame. Now, in conclusion, we have more than 3 decades of research and development to improve the IHRF. It is known to be the most precise or accurate reference frame available today. It's recommended by a number of scientific organizations. It is accessible everywhere, anywhere, thanks to the IGS products. The IHRF 2020 was a step further in improving the IHRF post-seismic deformation models provided to the users, and also seasonal signals provided in both the center of mass and center of figure frame. But we have to take into account or to note that global geodetic infrastructure needs improvement and sustainability. Most of current VLBI and SLR systems are old generation and needs upgrade. The International Association of Geodesy is not the owner of the geodetic infrastructure. There is an initiative within the United Nations called Global Geospatial Information Management on the GGRF, the Global Geodetic Reference Frame. It is an opportunity that our association should not miss. Thank you for listening.